Chapter 1: The Shadow of the Iron Curtain. Welcome to Synapse Daily. Today, we step back into the most pivotal year in human history, 1969. But we aren't looking at the Apollo 11 lunar module. We are looking at a continent still haunted by the echoes of heavy artillery and the crushing weight of two superpowers. Europe in 1969 was a pressure cooker. To the west, the American cultural machine was in full swing, exporting rock and roll and the dream of the frontier. To the east, the Soviet Union sat behind a wall of concrete in silence. There are 7 rockets ready to deliver either satellites or nuclear warheads. Between them lay a fragmented Europe, desperate to find a third way. This was the era of the technological gap. European leaders realized that if they didn't reach for the stars, they would remain forever under the boots of those who did. The European Space Research Organization, or ESRO, was born from this existential fear. It wasn't just about exploring the cosmos, it was about preventing a total intellectual bankruptcy. The air in the laboratories of 1969 was heavy. You could smell the soldering iron and the ozone. Scientists worked under the constant hum of massive mainframe computers that filled entire rooms. There was a specific tension in the hallways, a realization that every discovery made in a lab in Paris or Munich was being watched by eyes in Moscow and Langley. This wasn't just a quest for knowledge. It was a battle for the soul of European science. The Iron Curtain didn't just divide land, it threatened to divide the very sky above us. Chapter 2: The Birth of ESRO and the HEOS-1 Legacy. To understand the technical grid of 1969, we must examine the HEOS-1 satellite. Launched in the dying days of 1968 and becoming fully operational in 1969, HEOS stood for Highly Eccentric Orbit Satellite. The name itself tells a story of extreme engineering. NASA had the luxury of massive, heavy-lift rockets. ESRO had to be precise. HEOS-1 was a marvel of miniaturization for its time. It carried 7 different experiments from several European universities. Its mission? To travel further into the magnetosphere than any European craft before it. We are talking about an orbit that swung 225,000 kilometers away from Earth. The engineers faced a brutal reality: the Van Allen radiation belts. To reach deep space, the satellite had to pass through zones of intense radiation that could fry 1960s transistors in seconds. The shielding was a work of art. They used specialized aluminum alloys and gold-plated components to reflect thermal radiation and protect the delicate core of the machine. But the most difficult part was the magnetic cleanliness. HEOS-1 was designed to measure the tiny, flickering magnetic fields of the solar wind. This meant the satellite itself could not have any magnetic signature. Engineers had to build it using non-ferrous materials. Every screw, every wire, every connector was tested. If a single technician accidentally used a standard steel screwdriver during assembly, the entire mission would be blinded by its own magnetic noise. It was a cathedral of glass and wire, floating in the void, screaming back data that would change our understanding of the sun forever. Chapter 3: The Geopolitical Chessboard and the Brain Drain. In 1969, the most valuable resource in Europe wasn't oil or gold, it was the PhD. The brain drain was a silent crisis. The United States was aggressively recruiting the finest minds from the UK, France, and Italy. NASA's budget was an irresistible siren song for any young physicist. ESRO was the counter-move. It was a political gamble to prove that a unified Europe could provide a home for genius. But unity is a fragile thing. Inside the ESRO Council, the atmosphere was often as cold as the space they were trying to reach. The French government, under the shadow of de Gaulle's grandeur, pushed for total independence. They didn't want to rely on American Thor Delta rockets. They wanted a European launcher. The British, meanwhile, were cautious. They had the Blue Streak missile, a cancelled nuclear project they were trying to repurpose into a space booster. This created a two-speed Europe. While the scientists were trying to collaborate, the politicians were arguing over who would pay the bill and who would get the prestige. Despite this, the technology flourished. 1969 saw the birth of ESRO-2B, which focused on cosmic rays. It was a period of intense data diplomacy. Data from these satellites was shared across European borders, creating a new language of cooperation that bypassed the old wounds of World War II. The scientists spoke the universal language of mathematics, even while their governments spoke the language of suspicion. Chapter 4: The 1969 Summer of Science and Sabotage. July 1969. The world was transfixed by a single, grainy television broadcast from the Sea of Tranquility. But while Apollo 11's lunar module ignited its descent engine, a much more shadowed and desperate operation was unfolding in the high Arctic. For the engineers of ESRO, the moon was a distraction. The real war was being fought in the ionosphere, the invisible, electrified skin of our planet. ESRO-1A and 1B, known to the public as Aurora and Boreas, were launched into a polar orbit to study the northern lights. On the surface, it was a noble quest for atmospheric physics. But beneath the academic papers lay a terrifying military reality. In 1969, the North Pole was the shortest ballistic highway for a Soviet intercontinental ballistic missile, ICBM, aimed at New York or Washington. To detect these missiles, NATO relied on over-the-horizon radar. The problem? The Aurora Borealis, the very thing Europe was studying, created massive clutter and blind spots in these radar systems. The tension at the Tromsø tracking station in Norway was suffocating. Imagine a windowless concrete bunker, surrounded by miles of frozen tundra and the haunting silhouettes of radar dishes. Inside, technicians lived in a state of technical paranoia. They knew that every time a satellite passed over the polar cap, it was being swept by Soviet signal intelligence sensors. There were persistent reports of mysterious Soviet trawlers, small ships bristling with massive, out-of-place antennas lingering just outside Norwegian territorial waters. These weren't fishing boats, they were floating vacuum cleaners for data. Every pulse of telemetry from the ESRO satellites was sent via raw analog FM signals, a series of haunting, high-pitched warbles and chirps. The engineers had to catch these signals in a narrow 10-minute window as the satellite screamed overhead at 5 miles per second. If the signal flickered or was drowned out by static, was it a solar flare? Or was it active jamming from a KGB electronic warfare unit? In the summer of 1969, the beauty of the Northern Lights was nothing more than a tactical mask. Every electron measured by ESRO was a data point in a nuclear chess game, and the scientists were the unsuspecting pawns on the front line of the silent sky. Chapter 5: The Digital Dawn and the ESOC Nerve Center. By mid-1969, the sheer volume of data returning from the heavens began to overwhelm the old ways of manual calculation. This necessitated the rise of the European Space Operations Center, ESOC, in Darmstadt, West Germany. This wasn't just a building, it was a fortress of silicon and cooling fans. Inside, the roar of the air conditioning was the only thing that drowned out the frantic clicking of magnetic tape drives. The computers of 1969 were massive, room-sized monoliths. We are talking about machines like the IBM 360 series, which had less processing power than a modern car key, yet they were tasked with calculating orbital trajectories that had zero margin for error. A single misplaced punch in a cardboard card could send a satellite spiraling into the atmosphere to burn up over the Atlantic. Engineers worked in shifts of fire. They lived on caffeine and nicotine, their eyes bloodshot from staring at oscilloscope screens. They were developing the first real-time telemetry processing software, code that had to be written in assembly language, optimized to the last bit. There was no cloud, no internet. Every packet of data had to be physically recorded onto heavy magnetic tapes and moved by hand. This was the birth of the European digital DNA. In the heart of West Germany, surrounded by NATO bases, ESRO was building a digital nervous system that would eventually connect the entire continent. Chapter 6: The Failure of Europa 1 and the Lesson of Fire. The year 1969 was meant to be the year Europe finally shed its dependence on American heavy lifting. The mission was Europa 1, a colossal rocket that embodied the fractured but ambitious spirit of the continent. It was an engineering Frankenstein, a three-stage behemoth built by three nations that had been at war just 25 years earlier. The first stage was the British Blue Streak, a former nuclear missile, the second was the French Coralie, and the third was the German Astries. The launch site was Woomera, Australia, a vast, sun-scorched expanse of red dust and salt lakes. The heat was unbearable, reaching 45 degrees Celsius, making the liquid oxygen in the rocket's veins dangerously volatile. On the day of the F-8 launch attempt, the air was thick with the smell of kerosene and the gut-wrenching tension of national pride. The countdown was a multilingual ritual, a symphony of 10. Noof. Act 0. Ignition. The British first stage roared to life, lifting the 100-ton giant into the Australian sky. It was a perfect burn. The French second stage ignited precisely on schedule, pushing the craft into the upper atmosphere. The engineers in the control room held their breath. Success was seconds away. But then, catastrophe struck with cold, mechanical indifference. The German third stage, the brain of the rocket, failed to separate. For a few agonizing seconds, the rocket tumbled, a dying metal god fighting physics. Then, a massive, blinding orange fireball tore through the sky. The explosion was so powerful it shook the ground miles away. Millions of dollars and years of cross-border collaboration rained down as twisted, burning scrap metal across the desert. In the control room, there was only silence. The Americans at NASA looked on with pity, the Soviets with indifference. This wasn't just a mechanical failure, it was a psychological trauma. It exposed the unit friction of Europe. You couldn't just bolt three nations together and expect them to fly. This failure in 1969 was the lesson of fire. It taught the engineers that space is a singular, unforgiving entity that demands total integration. From the ashes of Europa 1, the seeds of the Ariane project were sown not out of success, but out of a desperate, scorched earth necessity to never fail like that again. Chapter 7: Solar Storms and the Nuclear Watch. In the autumn of 1969, as the leaves turned in Paris and London, the sun was reaching the violent peak of its 11-year cycle. It was a period of intense solar maximum, characterized by massive sunspots and hyperenergetic solar flares. For the scientists at ESRO, this was a golden opportunity to study the Sun-Earth connection. But for the military strategists in the Pentagon and the Kremlin, it was a countdown to a potential accidental apocalypse. A massive solar flare is essentially an electromagnetic pulse from space. In 1969, satellite technology was in its infancy, and its vulnerability to radiation was poorly understood. When a major flare hit the Earth's magnetosphere, it didn't just cause auroras, it caused radio blackouts and triggered false alarms in early warning systems. A solar proton event could mimic the electromagnetic signature of a high-altitude nuclear detonation. In the fragile, hair-trigger world of 1969, a misunderstood burst of solar radiation could be the glitch that launched 1,000 ICBMs. ESRO's HEOS-1 and IRIS satellites were the only neutral Sentinels monitoring these solar winds. The data they provided was dual use in its most terrifying form. While scientists published papers on magnetospheric density, military analysts were using that same data to calculate the first strike window. They needed to know when the sun would blind the enemy's radar, providing a cloak for a nuclear surprise attack. The scientists found themselves operating in a moral gray zone. Their laboratories were filled with data that could save the world or end it. Every solar particle they counted in 1969 was more than a number, it was a pulse check for a world on the brink of nuclear suicide. They were the nuclear watchmen, staring into the sun to ensure that a cosmic hiccup didn't start a third world war. The technology of 1969 wasn't just about reaching the stars, it was about preventing the stars from witnessing our extinction. Chapter 8: The Secret Language of TD-1A. As 1969 drew to a close, the engineering teams were finalizing TD-1A, the most ambitious European satellite of the decade. This was a monster of a machine, designed for high-resolution ultraviolet astronomy. But it had a problem that sounds like something out of a spy novel: the tape recorder. To store the massive amounts of data TD-1A would collect, it needed a high-capacity tape recorder that could survive the vibration of launch and the vacuum of space. In 1969, only a few companies in the world could build such a device, and they were all under heavy government contracts. The procurement of these parts involved back-channel negotiations and gray market technology transfers. Furthermore, the TD-1A used a stabilized three-axis control system, a revolutionary tech in 1969. This system allowed the satellite to stay perfectly still while hurtling through space, staring at a single star with pinpoint accuracy. The star trackers used to achieve this were so sensitive that they could, in theory, be used to stabilize a spy satellite looking down at the Earth instead of up at the stars. The line between science and espionage wasn't just thin. In 1969, it was invisible. As the decade ended, Europe had become a master of this invisible line, building tools of peace that were forged in the fires of the Cold War. Chapter 9: The Arctic Sentinels, Ground Stations and Frozen Telemetry. As we move into the final months of 1969, the focus shifts from the satellites themselves to the lonely men and women guarding the ground stations. ESRO's ESTRAC network was a triumph of logistical grit. The most critical node was the Kiruna station in Sweden, located far above the Arctic Circle. Why here? Because every polar orbiting satellite passes over the poles on every single revolution. Life at Kiruna in the winter of '69 was a test of human endurance. Engineers lived in a world of perpetual darkness, surrounded by massive, snow-covered parabolic dishes that hummed as they fought the freezing winds. These dishes had to track a tiny moving target across the sky with a precision of a fraction of a degree. If the hydraulic fluids in the dish mounts froze, the data was lost. These technicians were the front line of the Cold War's scientific front. They were often the first to see the data coming down, data that revealed the true state of the upper atmosphere. They operated in total isolation, connected to the rest of Europe only by fragile radio links and the occasional supply plane. It was here, in the sub-zero temperatures, that the concept of global monitoring was born. They weren't just watching stars, they were keeping a constant pulse on the Earth's own health, a precursor to the climate monitoring systems we rely on today. Chapter 10: The Great Miniaturization, Forging the Micro-Revolution. 1969 was the year the vacuum tube finally began to lose its grip to the silicon transistor in European space tech. The weight constraints of the Thor Delta launchers meant that every gram saved was a kilometer of altitude gained. This forced ESRO to push the boundaries of integrated circuits. European companies like Philips, Siemens, and Ferranti were pushed into a high-speed race to develop components that were space-qualified. This meant a chip had to survive 15 G of vibration, extreme thermal cycling from -150 degrees Celsius to +150 degrees Celsius, and the constant bombardment of heavy ions. In the clean rooms of '69, engineers were literally hand-soldering connections under microscopes, creating the first multi-layered circuit boards. This wasn't just about space. This was the foundation of the European computer industry. The techniques developed for the HEOS and TD1 as satellites flowed directly into the consumer market, leading to the telecommunications revolution of the 1970s. When you look at the sophisticated avionics in an Airbus today, you are looking at the direct descendant of the frantic, high-pressure miniaturization that happened in the labs of ESRO in 1969. Chapter 11: The French Defiance, The Path to the Kourou Spaceport. By December 1969, a major shift in the space geography of Europe was occurring. The French government realized that launching from Woomera, Australia, was too far and too politically complicated. They turned their eyes to a small, humid patch of land in South America, French Guiana. This was the birth of the Kourou Spaceport, CSG. Kourou was strategically perfect. Being close to the equator, the Earth's rotation gives rockets an extra kick of speed, about 460 meters per second. This allows for much heavier payloads. But building a high-tech spaceport in the middle of a jungle in 1969 was a monumental task. Engineers had to fight malaria, extreme humidity that rotted electronics, and the logistical nightmare of shipping entire rockets across the Atlantic. This move was a clear signal to the Americans and the Soviets: Europe was no longer content to be a junior partner. By establishing its own gateway to the stars, Europe was claiming its territory in the cosmos. Kourou became the symbol of European strategic autonomy. It was the place where the ghosts of colonial history met the dreams of the atomic age, and it remains the most important launch site in the world for commercial satellites today. Chapter 12: The Christmas of '69, A New World Order. On Christmas Eve, 1969, as the decade drew to a close, the mood at ESRO was one of exhausted triumph. The organization had survived its infancy. It had proven that scientists from nations that had been at each other's throats just 25 years earlier could work together to conquer the most hostile environment known to man. But the world had changed. The idealistic space for peace mantra of the early '60s had been replaced by a pragmatic, data-driven reality. The satellites launched in 1969 were now part of a global infrastructure.
They were the invisible web that made modern life possible. In a quiet ceremony at the Darmstadt Center, a senior engineer reportedly remarked that we went up looking for the secrets of the universe, but we found the secrets of our own survival.
This realization marked the end of the romantic era of space exploration and the beginning of the information age.
The data from 1969 showed that Earth was a fragile, interconnected system, a spaceship Earth that required international cooperation to protect.
Chapter 13, The Legacy, From ESRO to the Modern Frontier. As we conclude our journey through 1969, we must ask, what remains of the Cold War tech of ESRO? The answer is, everything. ESRO eventually merged with ELDO to become the European Space Agency, ESA, in 1975, but the ESRO spirit, the commitment to high-precision science and multinational cooperation, is the DNA of modern Europe. The telemetry protocols developed for HEOS-1 became the standards for the Galileo GPS system.
The thermal shielding designs for TD-1A protect the James Webb Space Telescope. The daring orbits calculated by the early computers at ESOC paved the way for the Rosetta mission to land on a comet.
1969 wasn't just a year of one giant leap on the moon.
It was a year of 1,000 small, brilliant steps across the European continent. It was the year Europe stopped looking back at its broken history and started looking forward to its cosmic future. We live in the world that ESRO built, a world where the stars are no longer distant lights, but reachable destinations. Thank you for listening to this deep dive into the shadows and the light of 1969.
This has been Synapse Daily. We explore the circuits of history to understand the currents of today. Like this video if you learned something new. Comment your thoughts below and subscribe for more fascinating stories.